You're about to watch the moment "maybe we're alone" stops being a serious sentence. Somewhere in the data from James Webb, one planet starts breaking all the rules, and suddenly that distant dot in the sky looks less like a destination and more like a "do not enter" sign. This isn't a story about finding a new home. It's a story about realizing someone else might already be living on the one we just discovered. But before we continue, please subscribe to the channel to give your support. Let's continue. How do you react when the first strong evidence for alien life doesn't show up as a spaceship in the sky, but as a strange pattern on your computer screen? You're in the 2020s, you're tired, you're going through a queue of James Webb exoplanet observations that should be routine. Then one of the entries is highlighted as high priority. The target name pops up: Kepler 442b. You've seen it before in papers, you've heard it in talks, but now it's sitting in your data pipeline, and this time something about it is different. You check the basics to anchor yourself. Kepler 442b is about 1,196 light-years away in the constellation Lyra. In metric, that's roughly 11 quadrillion kilometers. In imperial, about 7 quadrillion miles. Those numbers are so large, they crush any sense of travel. A regular jetliner flying at around 900 kilometers per hour, about 560 miles per hour, would need more than a billion years to cover that distance. A billion years ago, complex life on Earth was just getting started. So from the first second, you know this: you are not looking at a place we can visit. You are looking at a place we can only study through light. That alone already tells you this isn't local space. This is deep, deep background to our little human story. So why does this one observation, among thousands, suddenly matter so much? The first twist is that Kepler 442b is not a mystery object. Before Webb, you already knew a lot about it from the Kepler spacecraft. Kepler watched the star Kepler 442 and saw tiny regular dips in brightness about 0.25% each time the planet passed in front. From that, astronomers got its radius, roughly 1.34 times Earth's radius, so a bit bigger than our planet. Using population statistics and models, they estimated its mass at around 2.3 times Earth mass. That combination puts it right on the dividing line between a rocky super-Earth and a small, puffy mini Neptune. On top of that, its orbit looks promising. It sits in the star's habitable zone, the distance where a rocky planet with the right atmosphere can keep liquid water on its surface. Not too close, not too far. For years, Kepler 442b has shown up in most habitable exoplanet lists, not because we knew it had life, but because on paper its numbers looked better than most. You already liked this planet before Webb. It was a good bet. Now that you have Webb data, you revisit the gravity question, because that tells you how it might feel to stand there. With a radius about 1.34 times Earth and a mass about 2.3 times Earth, surface gravity works out to roughly 1.3 g, assuming it's mostly rock and water. If you weigh 70 kilograms on Earth, about 155 pounds, your body would effectively be supporting around 90 kilograms, close to 200 pounds on Kepler 442b. Walking, climbing, even just standing would take noticeably more effort. Your heart and muscles would have to work harder. But that same stronger gravity helps a planet keep a thick atmosphere and deep oceans over billions of years. So this isn't an instant deal breaker. In some ways, it's a plus. If the planet was already famous, the obvious question is, what changed when Webb aimed at it? The big change is the kind of information you now have. Kepler mainly gave you size and orbit. Webb gives you something more intimate, a first hint of the planet's air. When Kepler 442b passes in front of its star, a small ring of starlight passes through any atmosphere around the planet. Webb collects that light and spreads it out into a spectrum, covering wavelengths from about 0.6 to 12 micrometers. That's the infrared range, where many important gases leave clear, sharp fingerprints. You get a graph, wavelength along the bottom, how much light is blocked along the side. At very specific wavelengths, molecules like water vapor, carbon dioxide, methane, and ozone absorb light more strongly. That shows up as tiny extra dips in the spectrum. The idea is simple. If you know where each molecule absorbs and you see those patterns in the data, you can work backwards to figure out what the atmosphere is made of. In practice, it's very hard because the signals are small. You're looking for changes of tens of parts per million in the total light. That means you usually get noisy, jagged lines that you can argue about for months. But when you pull up Kepler 442b's spectrum, that usual frustration is missing. The line is still noisy, but the key features are clear enough that your brain recognizes them almost immediately. You see absorption features that match water vapor. You see signs that look like carbon dioxide. Then, as you fit detailed models, you start seeing evidence that methane might be present. And on top of that, there are hints of ozone, which usually means a significant amount of oxygen in the atmosphere of a rocky planet. Oxygen and methane together at noticeable levels are a big red flag in the best possible way, because they don't like to coexist for long without something constantly replenishing them. So now you face the question almost every exoplanet scientist quietly dreams and quietly fears. Could this be chemistry driven by life, not just by rocks and sunlight? You don't jump to that conclusion. You do the boring work first. You check instrument calibration, you compare with other targets observed in the same mode, you run the data through different reduction pipelines. The pattern stays. You ask whether the star's own activity could mimic these signals. That path doesn't explain the exact combination you see. You test non-biological ideas like strong ultraviolet light splitting water and leaving oxygen behind, or extreme volcanism filling the sky with methane. Each scenario leaves other fingerprints that you don't see in the spectrum. The more you try to kill the life explanation, the more it resists. At some point, this stops being just a technical puzzle and becomes a human moment. There's a Zoom call, late, with people from all over the world. Screens are shared, plots are shown, error bars are argued over. For a long time, everyone is careful with language. People say interesting, unusual, highly suggestive. Nobody wants to be the first to say the heavy word. Then one person finally breaks the tension and says it in a flat, almost tired voice. This looks inhabited. That sentence changes the room. Nobody screams, nobody cheers, but everyone knows the line has been crossed. You are no longer just talking about a promising candidate. You are talking about a planet where the entire atmosphere may be shaped by a global biosphere. That's the moment when the label Earth 2.0 feels too small. If Kepler 442b really has a stable, life-supporting atmosphere around a long-lived star, it isn't just a copy of Earth. It might be Earth 3.0. Older than Earth, calmer than Earth, with more time for life to start, adapt, and possibly reach levels of complexity we haven't seen here yet. And then the really unsettling thought clicks into place. If the biosignatures are real and strong, this world is not waiting for us. It is already occupied. We are not looking at free real estate. We are looking at someone else's home planet, even if that someone is only microbes or something far beyond that. So you sit there with that realization running laps in your head. A planet more than 1,000 light-years away, with gravity a bit stronger than Earth's, orbiting an orange star in Lyra, could be the first solid proof that life has taken root twice in our galaxy. From that point on, one question starts to dominate everything. Where exactly is this world in the Milky Way? And what kind of environment has it been sitting in for all these billions of years to allow this to happen? Because to understand how serious Earth 3.0 really is, you now need to zoom out and map its place in the real sky, next to us, on the grand galactic stage. So where exactly is Kepler 442b, and how close is this place that suddenly looks alive? You step back from the spectrum for a second and force yourself to treat it like any other object in a star catalog. Kepler 442b orbits a star called Kepler 442, a K-type main sequence star. In simple terms, it's a small orange dwarf, cooler and smaller than our Sun. Its mass is about 61% of the Sun's, its radius about 60%. The system sits roughly 1,196 light-years away from us in the constellation Lyra. In metric, that distance is about 11 quadrillion kilometers. In imperial, around 7 quadrillion miles. On a star chart, that's just a coordinate and a label. In physical reality, that is a gap so huge that even our fastest probes barely scratch the first decimal place. The only way to make that distance feel even slightly real is to use the galaxy itself as the measuring stick. Take the distance from the Sun to the center of the Milky Way, about 26,000 light years. Shrink that entire radius down until it's like a 10-kilometer jog, about 6.2 miles. On that scale, Kepler 442 isn't on the other side of the galaxy. It sits like an extra small half step along your route. On galactic terms, that's nearby. Same overall spiral arm, not some distant alien galaxy, not even a different region of the Milky Way. But here's the catch. Nearby on galactic scales still means completely unreachable with anything like current propulsion. For us, right now, this is a star we can point telescopes at, not a destination we can aim rockets at. So you know where it is in the sky, and you know what kind of star it orbits, but position alone doesn't tell you what it's like to live there. The next critical question is simple. How tight is this planet's orbit, and what kind of year does that create? Kepler 442b moves in close. It orbits at about 0.409 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers or 93 million miles. So Kepler 442b is at a bit more than 40% of that distance from its star. In other words, compared to Earth, it's about 61 million kilometers, roughly 38 million miles, closer to its star than we are to ours. This is a compact system. Because of that close-in orbit, its year is short. One full trip around Kepler 442 takes about 112.3 Earth days. So while you're used to a 365-day year, Kepler 442b wraps up a full orbit in a bit under 4 months. If there are seasons there, they come and go fast. You'd go through winter, spring, summer, and autumn in the time you're used to covering maybe one Earth season and a bit more. Agriculture, if it exists, would follow a completely different rhythm. Long-term climate cycles would stack on a much tighter orbital clock. A short year also means more frequent transits from our point of view, which is good for Webb because it gets more chances to watch starlight filter through that atmosphere. But a tight orbit can be dangerous around the wrong kind of star, so the next question you ask is, how bright is this star really, and how much energy actually hits the planet's top of atmosphere? Here, the star's nature becomes the key advantage. Kepler 442's luminosity, its total power output, is only 12% of the Sun's. It is dimmer, cooler, and more efficient over long timescales. So even though Kepler 442b orbits in closer, at about 40% of Earth's orbital radius, it doesn't get roasted. At that distance, the planet receives roughly 70% of the light and energy that Earth gets from the Sun. In metric energy terms, Earth gets on average around 1,361 watts per square meter at the top of the atmosphere. Kepler 442b gets about 950 watts per square meter. That's the raw stellar flux. Translated into everyday terms, that's like living under a dimmer, softer daylight, more like permanent high-latitude sunshine than harsh equatorial glare. The star's spectrum is shifted towards orange and red, so the daylight color would be warmer, less blue. For photosynthesis, for climate, for human eyes, that matters. Less ultraviolet, more red and near infrared. If you stood on the surface with the right gear, the sky and the star would look different, but your body would still feel a steady, usable level of light. Not a frozen dark world, not a blinding desert, but something in between. And that leads directly into the next key point. With that much energy coming in, what does the basic temperature balance look like before life or complex weather even get involved? Here you talk about equilibrium temperature, the starting point before greenhouse gases come into play. For Kepler 442b, that baseline comes out to about 233 Kelvin. In more familiar units, that's around minus 40 degrees Celsius, which is also minus 40 degrees Fahrenheit. That is cold. That's colder than most of Earth's surface, more like the interior of Antarctica or a deep Arctic winter. If the planet had no atmosphere or only a very thin one, you'd expect a frozen surface, with maybe small patches of seasonal melting at best. But planets with thick atmospheres don't just sit at their equilibrium temperature. Greenhouse gases like carbon dioxide and water vapor trap some of the outgoing heat and lift the surface temperature. On Earth, that greenhouse effect raises our average surface temperature by about 33 degrees Celsius, or 33 degrees Celsius. Without it, our planet would be a frozen snowball. If Kepler 442b has a moderate greenhouse effect of that order, you can take that -40 baseline and push it into the range where liquid water is stable over large regions. Add 30 to 40 degrees and you are suddenly flirting with temperatures around -10 to +10 degrees Celsius, roughly 14 to 50 degrees Fahrenheit. If the greenhouse effect is stronger, and many models for water-rich super-Earth suggest it could be, you can easily push average conditions into the 0 to 30 degrees Celsius, 32 to 86 degrees Fahrenheit. That's not tropical beach weather everywhere, but it's well inside the comfort zone for familiar biochemistry and for a stable, long-lived hydrological cycle. So when you put it all together, the picture becomes sharp. You have a planet orbiting a small orange star in Lyra, about 1,196 light-years away. The star is 61% the sun's mass, 60% the radius, and only 12% the luminosity. The planet sits at about 40% of Earth's orbital distance, gets about 70% of our sunlight, wraps up a year in 112 days, and has a cold baseline temperature that can be pulled into a liquid water range by any reasonable greenhouse effect. It is not a twin, but all the core numbers line up with one message. This is a world where a stable global ocean and a long-lived mild climate are entirely plausible. And now, on top of that, Webb is telling you that the air itself might already be shaped by life. With that groundwork in place, the pressure ramps up, because the next question is even sharper. Why did this particular planet, out of the thousands Kepler found, earn such a strong most habitable label even before Webb? And how did it turn from a theoretical favorite into the first real candidate for a living Earth 3.0? How did this one planet become the favorite long before Webb ever looked at it? Years before that weird spectrum showed up on your screen, Kepler 442b was already a quiet star of the exoplanet catalog. All we had back then were pixels, tiny dips in starlight recorded by the Kepler spacecraft. Every 112.3 days, the brightness of the star Kepler 442 dropped by about 0.26%. That's a change so small you'd never see it with your eyes, but Kepler's detectors picked it up over and over again. From the depth of that dip, you get the planet's size, because the amount of light blocked depends on how big the planet's disk is compared to the star. Run the numbers and you land at a radius about 1.34 times that of Earth's. Not a gas giant, not a Mars-sized rock, but a super-Earth, a bit bulkier than home. The obvious follow-up question is, if you only see the size, how did anyone get a mass? Before Webb, we didn't have a clean, direct measurement for Kepler 442b's mass, but we had statistics from hundreds of similar planets. Planets with radii around 1 to 1.5 times Earth's, in that regime, tend to fall into a mass range where they're mostly rock and maybe water, not huge hydrogen helium envelopes. So using those population studies, astronomers estimated its mass at around 2.3 times Earth's. That puts it right on the edge between two very different categories. On one side, dense, rocky super-Earths with solid surfaces and oceans. On the other side, many Neptunes with thick gas layers and no real ground to stand on. Kepler 442b sits on that knife edge, and that edge is exactly where you want to look if you're hunting for planets that could be cousins of Earth, not distant gas balloons. But size and mass alone don't make it special. A natural question is, out of all the planets Kepler found, why did this one specifically end up on so many best habitable candidates lists? The answer is its position in the habitable zone. For a cool K-type dwarf like Kepler 442, the habitable zone is closer in than for the Sun, but there is still a conservative safe strip where liquid water is possible over billions of years. Kepler 442b sits right in that conservative band, not at the inner too hot edge where oceans risk boiling, and not at the outer too cold edge where carbon dioxide can start to freeze out of the air. That alone would already put it near the top of any ranking. When teams build habitability indices that score planets based on how nicely they sit in this zone, Kepler 442b keeps showing up with a high score. It's not living on the edge, it's comfortably in the middle. You might ask, isn't that still just orbital geometry? Why were people already talking about it like it was something more, even before we saw its air? That's where modeling comes in. Recent work on super-Earths with sizes like Kepler 442b suggests many of them could hold a lot of water, far more than Earth. Depending on how and where they formed, and how many icy planetesimals crashed into them, they might end up as ocean worlds. For Kepler 442b, that means there's a real chance the planet doesn't just have oceans like ours, but global or near-global seas covering most or all of the surface. Not just blue patches between continents, but a planet where the main feature is water. The scale of that is easy to underestimate, so it helps to put some numbers on it. Earth's oceans are on average a few kilometers deep, with the deepest trenches going down to about 11 kilometers, around 7 miles. On an extreme ocean world model for a planet like Kepler 442b, you can get water layers tens to hundreds of kilometers deep. Picture an ocean column so tall that if you laid the distance from New York to Washington, D.C., roughly 330 kilometers or about 205 miles on its side, the water depth could rival that in extreme cases. At those depths, the pressure turns water into exotic high-pressure ice phases at the bottom, with a vast liquid layer above. If Kepler 442b is anything like that, then almost all of its biosphere could be ocean. That is a very different playground for life than Earth's mix of land and sea, and it comes with its own stability advantages. Oceans buffer climate, spread heat, and protect life from radiation. If the planet is sitting in the habitable zone, maybe an ocean world, orbiting a long-lived, relatively calm star, there's an obvious next question. How did the public conversation jump from good candidate to dramatic headlines like more habitable than Earth? That phrase sounds like clickbait, but it came from attempts to build composite habitability indices. These indices take several factors: orbital distance, stellar type, estimated surface temperature, potential water content, and stellar stability, and combine them into a single score. It's crude and not a direct measurement of anything, but it's a way to compare planets when you don't have full data yet. On some of these scales, Earth doesn't automatically win. A world around a more stable star with a longer main sequence lifetime and a sweet spot orbit can edge out Earth on paper. Kepler 442b is one of the planets that does. That doesn't mean it is actually better than Earth in every sense. We don't know its exact surface pressure, its detailed chemistry, its geological activity. Those can all make or break real habitability. But from a distance, when all you have are those few key parameters, Kepler 442b ticks enough boxes that the most habitable known exoplanet label kept appearing. So when Webb time was being allocated, this wasn't a random dart throw at a random world. This was pointing the most powerful infrared space telescope ever built at the champion seed in the habitability tournament, the planet that theory kept pointing to as one of our best bets. And that's what makes the current situation so intense. For years, this world was just numbers: transit depth, orbital period, estimated mass, modeled water fraction. Those numbers alone were enough to push it to the top of the list. Now you have a spectrum suggesting a complex disequilibrium atmosphere layered on top of that already strong case. A planet already labeled more habitable than Earth on some indices is now also the first one where the air itself looks like it might be maintained by a living biosphere. That combination is exactly why the tension keeps rising. The next piece of the puzzle raises an even sharper question. If the planet is this promising, how much credit goes to the planet itself and how much goes to the star it orbits? In other words, is Kepler 442b special mainly because of its own properties, or because its orange dwarf star, Kepler 442, provides a calmer, longer, more forgiving environment than our sun ever could? With Kepler 442b, a lot of the hidden advantage comes from the star itself. Kepler 442 is not a sun twin, it's a K-type dwarf, a bit smaller, a bit cooler, a bit dimmer. Its surface temperature is around 4,400 degrees Celsius above absolute zero, while the sun sits near 5,800, so it runs cooler by over 1,000 degrees. Its radius is only 60% of the sun's, so its surface area is smaller, and its light output is only 12% of what our star throws out. That cooler, smaller, dimmer profile shifts the star's light towards orange and red wavelengths instead of the harsh blue-white mix you get from the sun. For a planet close in, like Kepler 442b, that means something very specific for life. Less brutal ultraviolet, less constant high-energy radiation trying to tear apart molecules in the upper atmosphere. This matters because DNA, proteins, and many complex organic molecules are fragile under UV. On Earth, our ozone layer and magnetic field do a lot of work protecting life from the worst of the sun's output. Around the calmer, cooler star, the top layer of the atmosphere doesn't get hammered quite as hard. That doesn't mean there's no UV, but the balance shifts in a way that can make it easier for a thick atmosphere and delicate chemistry to survive over billions of years. For you, sitting here on Earth, that translates into a simple idea. If you had to pick a star type to host long-term life, not just quick, brutal bursts, a quiet K-dwarf like Kepler 442 is a safer bet than many other options. So the light is gentler, but how about time? How about the length of the story that life gets to play out under that orange star? This is where Kepler 442 really pulls ahead. A star like our Sun, a G-type dwarf, has a main sequence lifetime of roughly 10 billion years. The Sun is about 4.6 billion years old now, so it's almost at the halfway mark. That means Earth has already used up a big chunk of its stable window. In contrast, models for K-type dwarfs like Kepler 442 give main sequence lifetimes in the range of 18 to 30 billion years. That's roughly 2 to 3 times as long as the Sun. Same basic fusion physics, but running slower, more efficiently, over a much longer stretch. Now connect that to evolution. On Earth, it took about 4 billion years to get from the first simple life to a technological civilization that can point telescopes at distant planets. If Kepler 442 formed early in the galaxy's history, and if Kepler 442b had the right conditions from near the beginning, then life there could have had billions of extra years to start, stall, restart, diversify, and climb up the ladder of complexity. Take Earth's 4.5 billion year timeline, then tack on another 5 or even 10 billion years of stable conditions, and you're in a very different regime. From your point of view, sitting in the 21st century on Earth, that raises an uncomfortable question, because if life did get going there, it has had a huge head start on you. Of course, long life and gentle light don't help if the star is constantly throwing tantrums. So you have to ask, is Kepler 442 actually calm, or is there a hidden problem like the one we see around many red dwarfs? A lot of M-type red dwarfs, especially the ones that host famous exoplanets, are extremely active. They produce superflares, huge bursts of X-rays and UV radiation, and intense stellar winds. Atmospheres in tight orbits around those stars get blasted. Atmospheres can be eroded. Ozone can be destroyed. Surfaces can be sterilized again and again. When astronomers looked at Kepler 442's light curve from the Kepler mission, they didn't see the same flare chaos you see in systems like TRAPPIST-1. The star's brightness looks relatively steady, without constant violent spikes. That steadiness is not just an aesthetic detail. It feeds directly into whether an atmosphere like Kepler 442b's can survive for giga-years, billions of years. Less high-energy radiation means less stripping of the upper atmosphere, less chemical damage, fewer resets. The planet still has to deal with stellar wind and occasional flares, nothing is perfectly quiet, but compared to a lot of red dwarfs, this star is closer to calm middle age than angry teenager. Combine that with the fact that Kepler 442b is not pressed right up against the star, but in a somewhat wider orbit than many red dwarf planets, and you get lower overall exposure to those harsh conditions. From the point of view of a potential biosphere, this is almost like good weather insurance, fewer catastrophic events that can wipe everything out. So how does this calm, long-lived orange star stack up against the systems that used to dominate exoplanet headlines, the ones people used to hype as the best bets for life? Think about Proxima Centauri b, your closest known exoplanet neighbor at just over 4 light-years. That sounds great, very close, but it orbits a highly active red dwarf. Proxima throws frequent flares and blasts out strong X-ray and ultraviolet radiation. Its planet is in an extremely tight orbit, so close that it's probably tidally locked, with one side permanently facing the star. In that setup, the atmosphere is under constant attack. TRAPPIST-1 is similar in the sense that it hosts multiple Earth-sized planets in or near the habitable zone, which sounds amazing, but the star itself is a flare machine. Planets in those systems are basically sitting right next to a cosmic blowtorch. They might still hold on to atmospheres under some conditions, but the odds are worse, and the long-term stability needed for complex life is much harder to achieve. By contrast, Kepler 442b around Kepler 442 looks almost boring. The star is not too big, not too small, not too hot, not too dim. It doesn't throw constant violent fits. The energy output is stable over very long timescales. The planet sits at a distance where it receives a steady, moderate level of light. From the perspective of complex life, boring star plus stable flux is exactly what you want. Drama in the sky makes for pretty animations, but stability is what allows ecosystems to build layer after layer of complexity without being reset. And here's the part that should make you sit up a bit straighter. K-type stars like Kepler 442 are more common than Sun-like stars. If life really prefers this combination of long lifetimes, calmer light, and moderate energy, then our own situation around the hotter, shorter-lived G-type star might be the weird one. Earth could be the oddball, and planets like Kepler 442b could be closer to the standard blueprint for good biospheres in the galaxy. So when Webb picks up a strange, lifelike spectrum around the planet orbiting a K-dwarf, that might be a hint about where life usually finds its footing and where we should be focusing our search from now on. But all of this still leaves a very practical question hanging in front of you, one that turns the whole story from theory into hard data. How did Webb, sitting 1.5 million miles from Earth, actually sniff the air of a planet 1,196 light-years away and pull out those tiny molecular fingerprints that started this whole chain reaction? How do you actually read the air of a planet that's more than 1,000 light-years away when you can't see the planet itself as anything more than a speck? With Kepler 442, the whole trick starts with timing. You wait for the planet to move directly in front of its star from our point of view. During those few hours, the planet blocks a tiny fraction of the star's light, and more importantly, a thin shell of that light passes through whatever atmosphere the planet has. That shell is where all the information is. A small percentage of photons skim through the upper layers of the atmosphere, get absorbed at very specific colors by gas molecules, and then travel on toward Webb. Webb's instruments grab that already faint light and spread it out into a spectrum, like a highly precise rainbow, but in infrared, not visible colors. Instead of just red, green, and blue, Webb splits the light into thousands of very narrow wavelength bins. Then it measures how much light arrives at each bin during the transit, and compares it to how much arrives when the planet is not in front of the star. The differences it's looking for are tiny, on the order of tens of parts per million. That's like noticing that a stadium full of 100,000 people looks dimmer because a couple of dozen are holding up umbrellas. But if those umbrellas always appear at specific wavelengths tied to particular molecules, you can start to say what the atmosphere is made of. That's the basic transit trick. It sounds almost too simple. Watch the star, wait for the dip, compare before and during, and look for color-dependent changes. In reality, every step is hard. Instrument drift, detector noise, tiny pointing changes, background light from the telescope itself, all of that can hide or fake the signal. You're trying to subtract two huge numbers and keep only a tiny difference. But if you can do that cleanly, the atmosphere leaves its signature in those small residuals. And that's where you find your first clues that this might be more than just a dead rock. The next problem is brutal. There just aren't many photons to work with. Kepler 442b is faint. In visual terms, it's around magnitude 15. Your eyes, under a dark sky, can maybe reach down to magnitude 6. That means Kepler 442b is about 10,000 times dimmer than the faintest stars you can see without any equipment. Webb has a huge mirror, about 6.5 meters across, and extremely sensitive infrared detectors. But physics is physics. If the star is faint and the planet is small, the signal is photon-starved. So you can't just take one transit and call it a day. To get a spectrum that you trust, you have to stack multiple transits. For Kepler 442b, the orbital period is about 112.3 days. So you get at most 3 transits per Earth year if they're all visible to Webb and scheduled. In practice, you might need 10, 15, even 20 transits to push the noise down far enough. That's a program that stretches across several years of Webb's operational lifetime. Every transit you integrate for hours, collect as many photons as you can, then later you line them up in time and wavelength and average them. The real signal adds up, random noise averages out. The cost is huge amounts of telescope time, and the reward is a spectrum that actually says something about this planet's air instead of just looking like static. Once you have a stacked spectrum, the question becomes, what exactly are you looking for in that forest of data points? In the 1 to 5 micrometer range, these are wavelengths in the near infrared, you hunt for fingerprints of water vapor, methane, and carbon dioxide. Water vapor has strong absorption bands near 1.4 and 2.7 micrometers. Carbon dioxide has a key band around 4.3 micrometers. Methane leaves its marks at several spots in that region as well. Push out to 5 to 10 micrometers, the mid-infrared, and you start to see where ozone and nitrous oxide could show up, with ozone having a main band near 9.6 micrometers. Each of these molecules absorbs light very strongly at its own set of wavelengths, and weakly or not at others. So if the atmosphere contains them, the spectrum will have small dips in exactly those places. The important thing is not just one dip here or there. What matters is the pattern. Which dips appear, how deep they are relative to each other, how they line up with models for different gas mixtures. Life doesn't shout its presence with a single lifeline in the spectrum. Instead, you look for combinations of gases that shouldn't easily coexist in large amounts without some continuous source driving them out of chemical balance. That's where things start to move from chemistry to possible biology. Of course, spotting a pattern is not the same as trusting it. This is where the language of signal-to-noise and sigma levels comes in, and where the Kepler 442b program really pushes Webb to its limits. Signal-to-noise ratio tells you how big your signal is compared to the random fluctuations in your data. A higher ratio means more confidence. Sigma is a way of expressing how unlikely it is that what you're seeing is just noise pretending to be a signal. When astronomers talk about a 5 sigma detection, they mean that if there were no real signal, the odds of random noise producing what you see would be about 1 in 3.5 million. That's the sort of threshold you want before you claim you've detected something as important as a molecule tied to life. For a faint system like Kepler 442, getting to that level for multiple gases is extremely hard. In this fictional scenario, your program on Webb stacks hundreds of hours of observations. You calibrate every known systematic effect, track the star's own behavior, and squeeze the data until you're working at a precision of around 10 to 20 parts per million. At that point, every single photon matters. There's no slack. You're wringing information out of a faint orange star over 1,000 light years away, trying to see a planet-sized imprint in its light that's smaller than a rounding error. When you finally reach the point where the same absorption features keep appearing, transit after transit, instrument configuration after instrument configuration, and they reach those high sigma levels, the mood shifts. You're no longer wondering if there's a signal. You're now forced to confront what that signal actually means. And in the case of Kepler 442b, that's where things become uncomfortable, because the spectrum that emerges doesn't just look interesting, it looks wrong for a dead world. It looks like something is actively holding its atmosphere in a state that ordinary chemistry cannot explain. So the next step is unavoidable. With that spectrum in hand, molecule by molecule, band by band, what exactly did you see in Kepler 442b's air that made people in that late-night call start whispering the word biosphere instead of just atmosphere? How do you know you're not just seeing a weird but natural atmosphere, but something that's actively being held out of balance by life? When you finally lock in the best fit model for Kepler 442b spectrum, the combination of gases it spits out doesn't look calm or simple. It points to substantial oxygen, plus ozone that forms from that oxygen, at the same time as methane and probably nitrous oxide, all in the same atmosphere at levels you cannot just shrug off. On Earth, free oxygen is chemically restless. It wants to react with rocks, with metals, with volcanic gases. It only stays high in our atmosphere because photosynthetic life keeps pumping it out. Methane is even more fragile. In an oxygen-rich environment and under ultraviolet light from a star, methane gets broken down on timescales of decades. If you see both oxygen and methane present in solid amounts, long-term, something is constantly refilling at least one of them. That combination is what people mean by a disequilibrium atmosphere. Left alone, chemistry tends to push mixtures of gases toward a stable balance, where nothing big changes. When life is present and active, it can drive the atmosphere away from that balance by constantly producing and consuming gases. On Earth, plants, algae, and microbes pour out oxygen. Microbes in wetlands and animal guts produce methane. Without life, the oxygen and methane would react and settle down to far lower levels. With life, they coexist at much higher concentrations. So when your model for Kepler 442b needs a similar coexistence of oxygen or ozone and methane, plus hints of nitrous oxide, you're staring at a textbook biosignature combo. You're not saying we saw one gas that might mean life. You're saying we see several gases together in a mix that screams ongoing metabolism. That's the gut punch. But science doesn't stop at the punch. You now have to attack your own result. The obvious next step is to ask, are there non-biological ways to fake the signal? Could a dead planet, under the right conditions, produce the same atmospheric cocktail? So you start going through the usual list of false positives. First, oxygen without life. Intense ultraviolet light from a star can split water vapor in the upper atmosphere into hydrogen and oxygen. The light hydrogen can escape to space more easily, leaving oxygen behind. Over long times, this process can build up a lot of oxygen without any biology. But that kind of photochemical oxygen usually comes with a signature. You often see leftover carbon monoxide, and the detailed shape of the spectrum in some bands shifts in ways that don't match what you're seeing. When you run those models for Kepler 442b, they struggle to reproduce both the amount of oxygen and the rest of the spectral features at the same time. Next, you try to build the methane without life. Massive volcanic outgassing can release methane and other reduced gases from the planet's interior. On some worlds, that could give you thick methane-rich atmospheres. But volcanoes almost never work alone. They also vent carbon monoxide, sulfur dioxide, and other gases. Those have their own strong spectral fingerprints. You look for those in the Webb data. If volcanism were the main source of methane at the levels you're seeing, you'd expect clear carbon monoxide bands and sulfur-related signals. They're not showing up at the required strength. Chemical models keep failing to hold both high oxygen and high methane for long without some powerful, continuous source that looks a lot like biology. When your best non-biological scenarios keep breaking, you're forced back toward the uncomfortable conclusion that some kind of global metabolism may be shaping the sky. Even with the gas mix pointing in that direction, you still want to know, Is this the kind of planet that actually fits with a surface habitable to life as you know it? Or is this some strange gas-dominated mini Neptune with a weird, unreachable atmosphere? This is where the transit data does a quieter but important job. As the planet passes in front of the star, the depth of the transit changes slightly with wavelength. That tells you not just about which gases are present, but also about how high clouds and hazes sit in the atmosphere. For Kepler 442b, the wavelength-dependent changes point to a relatively shallow cloud deck over a denser, lower atmosphere instead of a huge, extended hazy envelope like you'd expect from a small gas planet. Put simply, the data fits better with a compact atmosphere over a solid or liquid surface, not with a deep, puffy gas layer. Combined with what you already know about its size and mass, that picture lines up well with an ocean-bearing super-Earth rather than a scaled-down Neptune. You're not resolving coastlines, you're not seeing continents, but you are getting strong, consistent hints that there's liquid water interacting with the air on planetary scales. Clouds not too high, not too thin, patterns that look like weather above an ocean world, not endless haze above a deep gas envelope. At this point, the question shifts one more time. You're no longer asking, is there any life at all? You're asking, how big is the impact of that life on the planet? The combination of gases, their relative amounts, and the overall structure of the atmosphere all point in the same direction. Whatever is driving this disequilibrium is not a tiny local process. It's not one lucky hot spring or a small patch of microbes hidden in one crater. On Earth, it was planet-wide photosynthesis, spread through oceans and onto land, that reshaped our sky into an oxygen-rich outlier. Cyanobacteria and later plants did this over hundreds of millions of years, turning our sky into a global signature of life that you could, in principle, spot from light years away. When you apply that logic to Kepler 442b, the conclusion is blunt. The spectrum you're seeing is best explained by a biosphere, not just life somewhere. A biosphere is a whole planet's worth of living systems interacting with rocks, water, and air, controlling the composition of the atmosphere at a global level. That's what your models are pointing to here. If they're correct, this planet is not just habitable in the sense that water could exist there and temperatures are okay, it is inhabited. The atmosphere you see is a product of ongoing biology on a planetary scale. That realization flips the narrative. This is no longer a question of potential, it becomes a question of status. Kepler 442b goes from good candidate to already taken, and that creates a new tension that you can't shake off. Now that you think you found a living Earth 3.0 around the calm orange star with stronger gravity and possibly a global ocean beneath your feet, how would your body and any human future cope with the physical reality of this alien but very real world? What actually happens to your body and to an entire planet's behavior when you turn Earth-like gravity up by about a third and then flood the world with ocean? Start with the simplest piece, weight. Kepler 442b is about 1.34 times Earth's radius and roughly 2.3 times Earth's mass. Put those together, and you get surface gravity around 1.3 g. That means every kilo of mass pulls on you as if it were 1.3 kilos. If you weigh 70 kilograms here, roughly 155 pounds, your body effectively weighs about 90 kilograms there, close to 200 pounds. If you can comfortably deadlift your own body weight on Earth, that same lift on Kepler 442b would feel like someone quietly strapped an extra 20 to 30 kilograms, about 40 to 65 pounds, onto your back every time you stood. Walking uphill hurts more, jumping is pathetic, your heart has to work harder to push blood around, and your skeleton carries more stress every second you stand. So you might ask, doesn't that make the planet hostile to humans by default? It would definitely be tough. Long-term, unmodified humans might face serious health problems, joint wear, circulation issues, faster fatigue. But from the planet's point of view, that extra gravity is an asset. Stronger gravity helps keep a thick atmosphere and deep oceans locked in for billions of years. It makes it harder for gas to leak off into space. It also affects how air and water stack up vertically, and that changes how weather and climate behave. That's where the next layer of weirdness comes from. Take the atmosphere. On Earth, there's a quantity called the scale height, which is just a way to say how quickly air thins with altitude. Roughly, it's the height over which the pressure drops by a factor of about 2.7. For Earth, that scale height is around 8.5 kilometers, about 5.3 miles. Climb that high and the air pressure is a lot lower, which is why high mountains feel thin and cold. On Kepler 442b, with gravity at about 1.3 g and similar temperatures, the atmosphere is more tightly packed. The scale height is smaller. Air pressure drops faster as you go up. For the same surface pressure as Earth, that means mountains, in terms of how quickly the air thins, would feel shorter. You don't have to go as high before the air thins out to the same degree as on a tall Earth mountain. But there's another knob you can turn: surface pressure itself. A water-rich super-Earth may well have a denser atmosphere than ours to begin with. Combine higher pressure with higher gravity, and you get thick, heavy air near the surface, maybe feeling almost soupy and breathe, with strong density gradients as you move upward. Those gradients can drive very fast winds at higher altitudes, where the air thins and flows more freely. Weather there might be more intense in the upper atmosphere, with powerful jet streams and storm systems that move huge amounts of heat around the planet. Then there's the big structural question. If this really is an ocean world, how deep do those oceans go, and what does sea level even mean? On Earth, our deepest ocean trenches drop to around 11 kilometers, about 7 miles. Our average ocean depth is more like 4 kilometers, about 2.5 miles. On a super-Earth like Kepler 442b, if it formed with a high water content, models suggest oceans that are tens to even hundreds of kilometers deep. Imagine a water column so tall that if you took the distance from New York to Washington, D.C., roughly 330 kilometers or about 205 miles, and turned it upright, the deepest parts of the ocean could be in that ballpark in extreme cases. At those depths, pressure becomes extreme. Water stops behaving like the liquid you know and starts forming high-pressure ice phases, like Ice 6 and Ice 7, which are solid but denser than liquid water. So beneath the liquid ocean, there could be a thick shell of these exotic ices, sitting between the liquid water and the rocky mantle below. That has a huge consequence. On Earth, our plate tectonics are driven by direct contact between rock and water in many places, and by heat flow through a thinner water layer. On Kepler 442b, a deep ocean capped by high-pressure ice might block that direct rock-ocean interaction. You could end up with little or no Earth-style plate tectonics at the surface. Instead of mountains and continents moving around, the main theater for geology and chemistry that matter to life might be the ocean itself. Circulation patterns, under-ice currents, hydrothermal activity where the high-pressure ice meets the mantle. So then you ask, if the ocean is that deep and the star is dimmer, does the surface just freeze? This is where the temperature story kicks in. The equilibrium temperature we talked about earlier, around 233 Kelvin, is a theoretical baseline. In more familiar terms, that's about minus 40 degrees Celsius, which is also minus 40 degrees Fahrenheit. That's what you get if you treat the planet like a bare rock or a simple reflector, with no greenhouse blanket. Real planets with thick atmospheres don't behave like that. Greenhouse gases such as carbon dioxide, water vapor, and possibly others like methane trap some of the outgoing infrared radiation and push the surface temperature up. On Earth, this greenhouse effect raises our average temperature by about 33 degrees Celsius. If Kepler 442b has a similar or slightly stronger effect, adding say 40 to 60 degrees Celsius to its bare equilibrium temperature, you move from minus 40 up into a range between about 0 and plus 20 degrees Celsius, roughly 32 to 68 degrees Fahrenheit. That is chilly compared to tropical beaches, but absolutely fine for liquid water oceans, active weather, and robust oxygen-breathing metabolisms. In fact, slightly cooler average temperatures combined with a deep ocean and a stable star can be very good for long-term climate stability. You avoid constant near-boiling extremes and get a world that stays in the cool but comfortable zone for billions of years. Put all of this together and you get a planet that would feel heavy under your feet, thick in your lungs, and vast under your ship if you ever found a way to float on its ocean. Gravity pulling a bit harder, air more compact, seas possibly stretching down into darkness far deeper than anything on Earth. It's not a gentle Earth clone, it's a tougher, denser version of habitable, tuned more for stability than for human comfort. But from evolution's point of view, that's not a bug, that's a feature. Stronger gravity in deep oceans can buffer changes, protect life, and keep things running smoothly longer than our own planet can manage. And that leads straight into the next unsettling question. If the planet's gravity, oceans, and temperature create this kind of fast but stable environment, what happens when you compress the entire orbit down to a 112-day year? How do seasons, day-night cycles, and global climate bands behave under an orange sun when everything, including time itself, runs on a tighter loop than we're used to on Earth? How does a planet feel when its entire year is squeezed into 112 days while its sky glows under a dim orange star instead of our bright yellow sun? Start with the basic clock. Kepler 442b completes one full orbit in about 112.3 Earth days. That means everything tied to the planet's position around its star, seasons, orbital climate cycles, changes in sunlight, runs more than 3 times faster than on Earth. If Kepler 442b spins roughly once every 24 hours like Earth, you get normal-length days and nights, but a year that's only about 4 of your months long. Winter, spring, summer, autumn, all packed into a tight loop that finishes before you've even finished the school term back home. Now, we don't actually know the rotation period, and that's a big deal. If the planet is partially tidally braked by its star, its day could be much longer than 24 hours, maybe dozens of Earth hours, maybe many Earth days. That would change everything about weather, storms, and how heat is moved from dayside to nightside. The important clue is its orbital distance. Kepler 442b orbits at about 0.409 astronomical units, a bit beyond the distance where we expect full tidal locking for this star, roughly 0.36 AU. That suggests a good chance it still spins, not with one face frozen towards a star forever, but with a real day-night cycle. Maybe slower than ours, maybe not, but likely not the eternal noon versus eternal midnight situation you get around many red dwarfs. For a biosphere, that's a big advantage. A rotating world spreads heat, air, and moisture around the globe. So what kind of climate bands form on a planet like this under an orange K-type star that sends out less energy per square meter and a different mix of wavelengths? The star is dimmer and redder. That means less overall power and less blue and ultraviolet light compared to the sun. Scattering in the atmosphere depends strongly on wavelength. On Earth, short blue wavelengths scatter more, which is why our sky is bright blue. On Kepler 442b, with more of the incoming light pushed towards orange and red, Rayleigh scattering is weaker. The sky could be more muted, less saturated blue, maybe a pale blue-gray or slightly different tint depending on the exact atmosphere. Clouds respond to this different energy budget too. Under a redder star, more of the energy comes in at wavelengths that can be absorbed deeper in the atmosphere, or even at the surface, instead of bouncing off high reflective clouds. So you might get cloud decks that sit lower, with more heat trapped in the lower atmosphere instead of high up. That can shift where storms form, how strong they get, and how efficiently heat is moved from the equator towards the poles. The whole climate engine is still driven by starlight and rotation, but the tuning is different because the light fueling it is shifted towards red. Then there's the ice line, the boundary between regions that stay mostly frozen and regions that can maintain liquid water. Kepler 442b gets about 70% of the sunlight Earth does, on average. That lower input means ice can survive closer to the equator than here. The snow line creeps down from the poles. Instead of narrow polar ice caps and wide warm belts, you might get thick, permanent ice at high latitudes and broad, cool, temperate bands in the mid-latitudes. The equatorial region might not be tropical jungle. It could swing between cool and mild depending on season. Think less planet-wide tropics, more planet-wide Iceland or global North Atlantic coast. Cold oceans, frequent storms, cool summers, and winters that bite but don't always completely seal everything in ice. Of course, local details matter a lot. If Kepler 442b is a deep ocean world, water has a huge heat capacity and resists rapid temperature swings. That means even with a 112-day year, the oceans can smooth out the seasonal extremes. The star might move from closer in to farther away over that orbit, but the water takes time to warm up and cool down. That delay can make seasons feel less extreme on the surface, more like gentle shifts instead of violent swings, especially near the equator and mid-latitudes. The short year just means those smoother cycles loop more quickly. Plants, if they exist, might adapt to fast seasonal cues. Migration patterns, breeding cycles, and ecosystem timing would all be compressed into this tighter orbital schedule. You can also flip the question and ask, what if the rotation is slow? Longer days and nights mean longer heating and cooling periods within each day-night cycle. The day side could warm more before sunset, and the night side could cool more before dawn. That tends to drive strong winds as air rushes from hot regions to cold ones. On a world with a thick atmosphere and strong gravity, you might see powerful, large-scale storm systems locked to the day-night pattern if the rotation is very slow, or Earth-like jet streams and storm tracks if it's closer to a 24-hour spin. We don't know which is true, but we do know the planet doesn't sit in the worst-case, fully locked regime, and that alone pushes it toward more even, rotating climate patterns. All of this plays out over not just 1 year, but billions of years. That's where the star's stability comes back into the story. K-type stars like Kepler 442b evolve more slowly than the Sun. Their brightness increases over time, but at a slower rate. For a planet in the habitable zone, that means the zone itself moves outward more slowly. Earth is on a timer. As the sun brightens, our planet will eventually be pushed into a runaway greenhouse state, where oceans evaporate and the atmosphere becomes thick with steam and then broken water vapor. That is likely hundreds of millions to a couple of billion years away, but the trend is there. Kepler 442b, by contrast, sits in a zone that changes more gradually. The room for error is bigger, and the time before things go off the rails is longer. If there is any kind of carbon-silicate cycle, where CO2 in the atmosphere reacts with rocks, gets buried, and then returns through volcanoes, that gives the planet a built-in thermostat. Oceans and atmosphere can work together to buffer changes, releasing or absorbing greenhouse gases as needed. On Earth, this feedback helped keep us habitable despite a faint young sun and later changes. On Kepler 442b, under a slower evolving star, the same kind of feedback could keep the planet in a just right state for absurdly long stretches, far longer than Earth's habitable window. From evolution's point of view, a 112-day year under a calm orange star is not chaos. It's a very stable, repeatable framework. Seasons come and go quickly, but predictably. Climate bands settle into patterns and stay there for giga-years instead of being jerked around by a rapidly changing star. That gives whatever lives there a long runway to adapt, diversify, and possibly climb to complexity levels well beyond what we see on Earth right now. For you, that raises the tension another notch, because you're no longer just thinking this world could host life. You're now staring at a planet with strong gravity, deep oceans, a fast but stable climate cycle, and a star that offers billions of extra years compared to our own. So the next question hits harder. If Kepler 442b's environment is this friendly to long-lived biospheres, and we already see an atmosphere that looks alive, is it really just microbes in an endless ocean, or something that knows it exists and can change its planet on purpose? The first thing you have to accept is that a strong biosignature is not the same as a civilization. Your Webb spectrum tells you that something is metabolizing at planetary scale, reshaping the atmosphere in a way that screams global life. But that only tells you there's a biosphere. It does not prove there are cities, no space stations, no radio towers, no hands or tools. On Earth, we had a planet-wide biosphere for billions of years before a single radio transmitter ever existed. For most of our history, Earth would have looked like inhabited but quiet from light years away. Kepler 442b might be in that phase right now. So you have to separate two questions in your head. One, is there life? Webb spectrum is pushing you toward yes. Two, is there technology? Is there a civilization that's gone beyond just surviving? That second question needs different tools and different strategies. The biosignature work is about passive chemistry. The technosignature search is about deliberate or byproduct signals that only technology produces. The unsettling part is that once you admit the planet is almost certainly alive, the odds that some lineages have had enough time to climb up to intelligence stop feeling ridiculous. Now it becomes reasonable to ask, if there's a technological species there, can we pick up the traces from 1196 light-years away? The first place people look is still the classic one, radio. Radio SETI takes big dishes or arrays and points them at Kepler 442, then listens for narrow-band signals, very pure tones at specific frequencies. Nature almost never produces ultra-narrow signals that sit in one frequency channel and stay there. Technology does. Our own transmitters, radars, and broadcasts leak narrow-band radio all the time. So Radio SETI looks for that kind of unnatural sharpness cutting through the noise. You scan different frequency bands, integrate for hours, and see if anything pops up that looks too clean and too focused to be a random astrophysical process. You can extend the same idea to light. Optical SETI searches for extremely fast, intense laser pulses, brief flashes of focused light that stand out against the constant glow of the star. A powerful laser aimed even roughly in our direction could, in principle, be detectable over interstellar distances. Then there's the more speculative approach, searching for mid-infrared excess from the system, a bit of extra glow at wavelengths where warm structures radiate waste heat. In theory, a civilization building megastructures, orbital habitats, or giant energy collectors could throw off waste heat that shows up as an abnormal bump in the system's infrared spectrum. In practice, at a distance of 1,196 light-years, and with a modest K-type star, that is extremely hard to pick out. The signal would be buried under the star's own infrared output and the limitations of our current telescopes. If you really want something that feels like pollution, you move back to the atmosphere and look for technosignatures there. Advanced technology doesn't just make radio waves, it also makes chemicals that nature rarely produces in large amounts. On Earth, industrial processes created chlorofluorocarbons, CFCs, for refrigeration and other uses. These molecules have strong, distinctive spectral features in the mid-infrared. Other industrial pollutants do as well. The key point is that you don't need to see individual factories or cities. If a civilization uses enough of a long-lived pollutant, it spreads around the planet and becomes a thin layer in the global atmosphere. From light years away, that can be detectable as a set of extra absorption or emission features that don't match any known natural chemistry. Right now, Webb is not quite sensitive enough to pick up a thin layer of CFC-level pollutants in the air of a small planet around a faint K-dwarf at this distance. You would need a bigger space telescope, with more collecting area and instruments tuned to those exact wavelengths. But in this scenario, you can already see how the strategy changes. Once you know the planet is alive and has an atmosphere you can read, future missions can be designed to stare at Kepler 442b specifically, in the right bands, hunting for those unnatural chemical lines. It's like moving from "we can see there's air and water" to "we're looking for the fingerprints of industry." The most dramatic technosignature test, the one everyone loves to talk about, is also the least practical right now: night side lights. In principle, if you had a gigantic space telescope with insane resolution and contrast, you could try to separate the day side and night side brightness of Kepler 442b and see if the night side is brighter than it should be. Natural night sides reflect almost no starlight. They're mostly dark except for a thin glow from air glow and lightning. A planet covered in city lights, power grids, and illuminated infrastructure would leak a tiny amount of artificial light on the dark side. That glow would have a different spectrum and pattern than reflected starlight. If you could map those patterns over an orbit, you could say, this is not natural. But in practice, with Kepler 442b at roughly 11 quadrillion kilometers, about 7 quadrillion miles away, and with our current hardware, this is science fiction level hard. Webb cannot do it. Even the next generation of telescopes we're planning can't do it in a straightforward way. You'd need an enormous space interferometer or a vast segmented telescope that doesn't exist yet. Still, the fact that people are seriously laying out the math for detecting city glow on a world more than 1,000 light-years away tells you how much this Earth 3.0 breaks your old sense of isolation. A few decades ago, the idea of even knowing if such a planet existed was ambitious. Now, you're talking about whether its dark side has streetlights. So you're stuck in this strange position. The biosignatures make it hard to deny that Kepler 442b is occupied by life. The technosignature searches you can do today might come up empty, not because there's no civilization, but because your tools are still too weak. Or they might show something odd, a narrow band spike, a strange chemical band, a hint of structure you can't explain yet. Either way, the planet no longer feels like a blank canvas. It's a place with its own timeline, its own experiments in evolution, possibly its own history of technology. And that forces you to ask one more uncomfortable question. If this world is so promising, why wasn't our first big hit Proxima b, or TRAPPIST-1, or one of the other famous nearby systems that got all the attention before? What exactly makes Kepler 442b beat out our other favorites in the race to be the first confirmed living exoplanet? Why did the first strong, "this looks alive" signal show up on a planet more than 1,000 light-years away instead of the famous nearby world everyone kept talking about for years? On paper, it feels backwards. Proxima b is right next door, at 4.2 light-years. Distance-wise, that's a dream, about 40 trillion kilometers, roughly 25 trillion miles. In interstellar terms, that's next door. But the proximity hides a serious problem. Proxima is a flare-happy red dwarf. It's small, cool, and extremely active. It throws frequent flares, powerful bursts of X-rays and UV light, and it has a harsh stellar wind. Proxima b orbits very close in to stay in the habitable zone, so it hugs that star tightly. When you put a planet that close to a volatile red dwarf, several bad things happen at once. First, tidal forces likely slow the planet's rotation until it becomes tidally locked or nearly so, with one hemisphere always facing the star and the other in permanent night. That alone stresses a climate because you're trying to move heat from an eternal day side to an eternal night side. Second, the constant bombardment from flares, X-rays, and high-energy particles can erode an atmosphere over time, stripping it away if the planet's magnetic field and gravity can't keep up. Third, the intense UV can break apart molecules, including ozone, leaving the surface exposed to more radiation. So yes, Proxima b is close. That makes it attractive as a future target for probes and direct imaging. But in terms of long-term, gentle conditions for complex life, Kepler 442b looks better. It trades proximity for stability. Around a calmer K-type star, at a wider orbit with less vicious radiation, and a slower-moving habitable zone, Kepler 442 sits in a safer spot for an atmosphere to survive, and for a biosphere to persist. For simple microbes that can handle extreme conditions, Proxima b might still be fine. For a long-lived, planet-wide biosphere that slowly builds up enough oxygen and methane to be visible across a galaxy, Kepler 442b has the advantage. Now look at the TRAPPIST-1 system, which was the poster child for compact habitable system for years. TRAPPIST-1 is an ultra-cool M-dwarf with 7 Earth-sized planets packed into orbits so tight you could fit them comfortably within Mercury's orbit. Several of those planets lie in or near the habitable zone. When this system was announced, it was like hitting the jackpot. Multiple potentially rocky worlds, some with the right amount of starlight, all in one place. From a telescope time perspective, it's efficient. One star, many targets. But again, the star is the problem. TRAPPIST-1 and stars like it show repeated superflares, events that release enormous amounts of energy in short bursts. These can hammer planetary atmospheres with high-energy radiation, especially when the planets are very close in. Over long times, that can strip ozone layers, which protect surfaces from ultraviolet radiation, and can even drive off lighter molecules from the atmosphere itself. When planets are packed tightly, gravitational interactions and tides complicate things further, potentially causing heating and orbital changes. Kepler 442b, by contrast, has a slower, wider, simpler setup. One planet in the habitable zone, not a whole chain. A K-type star that's calmer and less flare-prone than a tiny M-dwarf. An orbit far enough out that the planet isn't hugging the star. If you're betting purely on which world is more likely to still have a thick, water-friendly, life-supporting atmosphere after billions of years, then Kepler 442b wins. The TRAPPIST-1 planets are exciting laboratories, and they might still host life, but their star is actively working against them. Kepler 442, in contrast, is more like a long-term landlord that mostly leaves its tenant alone. Then there's Kepler 452b, the one that was sold as Earth 2.0 in a lot of press releases. It orbits a sun-like star at roughly an Earth-like distance. That sounds perfect at first glance, but Kepler 452 star is older than the Sun, possibly by more than 1 billion years, and likely drifting toward a brighter, subgiant phase. As sun-like stars age, they gradually increase in luminosity. That pushes their habitable zones outward. A planet that starts out comfortably in the middle of a zone can slowly slide toward the inner edge, or things get too hot. For Kepler 452b, that means there's a real chance it's already on the way toward a runaway greenhouse state. Surface oceans might be evaporating or already gone. Its atmosphere might be shifting toward high humidity and thick steam, an early version of what Venus went through. Even if it had an Earth-like climate in the past, that phase may be ending. Kepler 442, being cooler and a different type, brightens more slowly. Its habitable zone moves outward much more gradually, and Kepler 442b sits in a position that stays good enough for longer. So while Kepler 452b got the flashy nickname, Kepler 442b may actually have the longer stable window, which is exactly what evolution needs. All of this can feel like cherry picking, so you might ask, is this just storytelling, or did the numbers actually favor Kepler 442b even before Webb looked at it? That's where habitability indices come in. Different research groups have built composite metrics that fall together things like stellar type, orbital distance, equilibrium temperature, estimated water content, and stellar stability. You assign each parameter a score based on how friendly it looks to Earth-like life, then combine those into an overall index. It's not perfect, and it doesn't capture every detail, but it gives you a systematic way to rank candidates instead of going on vibes. When people ran these indices across the catalog of known exoplanets, Kepler 442b kept landing near the top. It has a good orbital distance for its star, a temperature estimate that fits liquid water with a reasonable greenhouse effect, a mass and radius that lean toward a rocky or water-rich composition, and a host star that's long-lived and relatively calm. Proxima b loses points for its nasty star and likely tidal locking. TRAPPIST-1 planets lose points for extreme stellar activity and tight packing. Kepler 452b loses points for its star's age and brightening trend. Kepler 442b, while far away, keeps checking more boxes more cleanly. So when telescope time for Webb was being divided up and teams had to decide where to aim the most sensitive exoplanet instruments ever launched, Kepler 442b was not a random pick. It was on multiple top candidate lists. The fact that it's 1,196 light-years away is a practical annoyance, not a scientific red flag. And that's the key point. Given what we knew, if Webb was going to find a strong, clean biosignature anywhere in its first generation of observations, Kepler 442b was always one of the most likely places for that first big hit. In this scenario, that's exactly what happened. Once you accept that, the question shifts from why here to what next? Because now you're not just comparing planets, you're staring at a real, living world under an orange sun, more stable than Earth, probably older than Earth, with more time for evolution to run wild. The next thing you naturally want to know is simple and unnerving at the same time. If life has been playing with that environment under a dimmer, redder star for billions of extra years, what does that life actually look like? How does photosynthesis work there? What colors would dominant organisms be? And how would deep, high-pressure oceans and altered mutation rates change the way complex life evolves under that orange sky? If the star is different, does life still end up looking anything like the stuff you know? Or does an orange sun rewrite everything from the color of plants to the way evolution runs its experiments? Kepler 442 is a K-type star, and that changes the rules right from the start. It puts out more of its energy in orange, red, and near-infrared light and less in blue and ultraviolet. On Earth, chlorophyll grabs red and blue light and mostly reflects green, which is why plants look green to you. Under an orange star, that setup isn't optimal anymore. A life form that wants to squeeze every bit of usable energy out of the light field around Kepler 452b has strong reasons to shift its pigments. Photosynthetic systems there would probably tune themselves to longer wavelengths, roughly in the 600 to 1000 nanometer range, where the star's output is strongest. Instead of reflecting a lot of green, they'd soak more of it up, plus deep red and near infrared. That pushes you toward darker, more light-hungry colors. Dominant phototrophs, plant equivalents, whether they're algae, mats, or something completely alien, might look dark red, almost black, or deep purple. Black is especially attractive because it basically means absorb almost everything and waste very little. A forest on Kepler 452b, if it exists, might not look like our bright green forests. It might look like a matte, dark surface that barely reflects anything because every photon is precious. That sounds cosmetic, but it changes the physics of the surface too. Darker phototrophs absorb more energy, which affects local heating, air circulation just above the ground or ocean, and even cloud formation. You end up with feedbacks where biology and climate shape each other. On Earth, our vegetation already plays that game. Forests and ice reflect different amounts of light. But under an orange sun with darker pigments, that effect could be even stronger. The whole light budget of the planet shifts, and life adapts not just to survive in it, but to exploit it aggressively. But if the light is softer and redder, what does that do to the mutation engine that drives evolution in the first place? UV radiation is one of the main ways DNA and similar molecules get damaged. It creates breaks, crosslinks, and other errors that, if not repaired properly, turn into mutations. Kepler 442's lower UV output means less of that direct DNA smashing energy coming in. That can be good for stability. Fewer random lethal hits, fewer mass sterilization events. But it also changes how the atmosphere is built. Some important molecules, like ozone, form through photochemical reactions driven by UV. With less UV, you may get less ozone production by default, unless other pathways compensate. Life under an orange sun might evolve with weaker UV repair systems because the pressure to maintain heavy-duty repair machinery is lower. At the same time, organisms might become more sensitive to other sources of damage, like cosmic rays or the occasional flare that does punch through. The mutation rate dial is effectively set to a different position. Maybe you get fewer random changes per generation from UV alone, which could slow some aspects of evolution. But you also have far more time to operate because the star is stable for tens of billions of years. Evolution can afford to run at a slightly slower mutation rate if it gets an extra 5 or 10 billion years of runtime. The balance between stability and variation is shifted, but the total time available to explore new solutions is vastly larger. Now layer that on top of the likely structure of the environment. If Kepler 452b is water-rich, you don't just have one ocean like Earth's, you have stacked, stratified ocean systems with extreme vertical differences. At the top, near the surface, water is in contact with the atmosphere. It's more oxidized, more mixed with gases like oxygen and carbon dioxide, and flooded with whatever light makes it through the clouds. Deeper down, as you go tens of kilometers, maybe up to 50 or 100 kilometers, that's roughly 30 to 60 miles, the light drops off, the pressure climbs, and the chemistry shifts. Lower layers can become more reduced, meaning they're richer in chemicals like hydrogen or hydrogen sulfide that can act as energy sources for certain microbes. If the ocean floor is in direct contact with the mantle in some places, or if there are gaps in the high-pressure ice that we talked about before, hydrothermal vents could spew hot, mineral-rich fluids into these deep waters. There, you'd get bizarre chemotrophic ecosystems, powered not by light but by chemical gradients. Think of something conceptually similar to Earth's black smoker communities, but scaled up in depth and variety. Above that, in the mid-depths, where the light is dim but not zero and the pressure is high but survivable, evolution might favor large, buoyant structures, plankton-like megastructures, rafts of living tissue, or colonies designed to hover at just the right depth where light, nutrients, and pressure line up. They could adjust their buoyancy by changing internal gas or fluid composition, rising and sinking through different chemical layers as conditions change. Near the surface, photosynthetic life does the classic job, capturing light, building biomass, releasing gases like oxygen or something analogous. Deeper down, layers of organisms feed on the rain of organic material falling from above, while others tap directly into chemical energy from vents and rock-water interactions. You end up with enormous vertical chemical gradients, where different metabolisms stack like layers in a cake, each exploiting a specific combination of light, pressure, and chemistry. That's not just a biosphere, that's an entire three-dimensional volume of water filled with nested ecosystems, from microscale to potentially very large organisms. With that kind of physical setup and a star that offers billions of extra years of stable conditions, the obvious question is, how far can complexity go? On Earth, it took about 4 billion years to go from the first simple life to a technological species broadcasting radio waves and launching telescopes. Most of that time was spent at the microbial level, with multicellular life only really exploding in the last half-billion years or so. If Kepler 442b had reasonably friendly conditions early on, and if life started there within the first few billion years of the planet's history, it could easily have had 6 to 10 billion years to run its experiments instead of our 4. That extra time is not a small tweak, it's a huge multiplier. It means room for multiple waves of complexity. Evolution could try something, hit a wall, collapse, and then try again under slightly different conditions. Entire eras of complex life could rise and fall before anything analogous to a technological civilization ever appears, if it ever does. Or maybe complexity saturates earlier, and the planet spends billions of years in a state where complex multicellular organisms dominate land, sea, or whatever its primary habitats are, without ever moving into tools and machines at all. Either way, the search space of possible life forms has had more time to be explored. From your perspective, sitting here with Webb data and models on a screen, that head start is the most unsettling part. If Kepler 442b only hosts microbes, then evolution has had a very long time to get stuck. If it hosts complex life, that life has had a very long time to spread, diversify, and adapt to every niche. And if it ever produced a technological species, that species has had a very long time to either wipe itself out, transform the planet, or quietly stabilize into something we barely know how to imagine. You're looking at a world where the clock has been running much longer than ours, under conditions that are in many ways kinder to long-term habitability than Earth's is. So the natural next question is harsh and simple. If somewhere on that distant ocean world, under that orange sky, there really is life that thinks and builds, what does it actually take for us to ever meet it, or even just send a probe that can skim past its star and send back a close-up photo? What do the hard numbers say about crossing 1,196 light-years of space, not in science fiction, but in terms of real speeds, real energy, and real timelines? So what does it actually take, in real numbers, to go from staring at a spectrum on a screen to sending anything at all across that ridiculous gap to Kepler 442b? Start with the simplest, harshest fact: distance and light speed. Kepler 442b is about 1,196 light-years away. 1 light-year is how far light travels in 1 year, moving at about 300,000 kilometers per second, around 186,000 miles per second. So when you say 1,196 light-years, you're literally saying light takes 1,196 years to cross that gap. That means any radio signal you send today at light speed would show up there nearly 12 centuries from now. A reply, if anyone answered immediately, would arrive almost another 12 centuries after that. You're not starting a back-and-forth conversation. You're carving a message into space-time, sending it, and trusting that some far future version of humanity, maybe 2,400 years from now, will be around to read whatever comes back. In terms of human lifetimes, that's not communication. That's time capsule exchange. So maybe you think, fine, forget chat. What about travel? We've already launched fast spacecraft. How bad can it be? Take something like the Parker Solar Probe. At its closest pass to the sun, it hits speeds of about 190 kilometers per second, roughly 430,000 miles per hour. That's insanely fast by our standards. But run the math against interstellar distances and it collapses. At that speed, just crossing a single light year would take on the order of 200,000 years. Multiply that by 1,196, and you get travel times measured in tens of billions of years. That's longer than the current age of the universe. If you want to cross 1,196 light years in a timescale that still feels like human civilization, say 10,000 years, you need a completely different speed regime. You're talking about average cruise speeds around 1/10 of light speed, about 30,000 kilometers per second, roughly 67 million miles per hour, sustained, not as a brief peak. That is far beyond anything our current chemical rockets or even advanced probe concepts can do. Everything we have now is crawling compared to what you need. Then you hit the energy wall. Pushing mass up to a significant fraction of light speed takes a staggering amount of energy. Take a modest 1-ton probe, about 1,000 kilograms. Accelerating that to 1/10 light speed gives it a kinetic energy on the order of a few quintillion joules. In words, that's several hundred billion joules. Human civilization today uses energy at a rate of a few times 10 to the 13 watts. Over a day, that's on the order of 10 to the 18 joules. So shoving a 1-ton probe to 1/10 light speed would cost you roughly as much energy as all of humanity uses in several days, maybe close to a week. And that's if you could convert energy to probe motion with perfect efficiency, which you absolutely cannot in real hardware. And that's just the acceleration. You also have to slow the probe down again if you actually want it to do more than flash through the Kepler 442 system in a fraction of a second. So in practice, the energy budget doubles, or you accept a flyby that collects whatever it can in a brief high-speed pass. Either way, once you start putting real numbers on it, interstellar travel to a target over 1,000 light years away stops looking like engineering and patience and starts looking like a boundary between physics and philosophy. It's technically allowed by the laws of physics, but what it demands from your technology, your energy infrastructure, and your time horizons is so extreme that it feels almost abstract. You can try to patch that with advanced propulsion ideas. Laser sail concepts, like the ones proposed for much closer targets, use huge ground-based or space-based lasers to push lightweight reflective sails to large fractions of light speed. Fusion drives could in principle get you higher exhaust velocities and better efficiency than chemical or fission-based systems. Antimatter concepts go even further, packing maximum energy into minimum mass. But all of these need infrastructure and control we simply do not have. For Kepler 442b's distance, you don't need just one new technology. You need a whole civilization-level shift in how we handle power, materials, and risk. And you need to sustain that over timeframes that span many generations. So, in any honest assessment of can we go there, the answer right now is no. Not just it's hard, but bluntly, not with anything close to what we have or even what we're seriously designing today. That doesn't mean you give up. It just means you recalibrate what going there means in your lifetime. You stop imagining starships for now, and you lean fully into the only thing you can send that actually travels at light speed and costs you no fuel once launched: photons. In practical terms, that means telescopes. Bigger mirrors, sharper optics, more stable platforms in space. You push for higher resolution spectra that can separate more atmospheric gases at more wavelengths with better precision. You design missions that can do direct imaging, physically block out the starlight with starshades or coronagraphs, and resolve the planet as a tiny dot next to its star. You build interferometers, multiple telescopes acting together as one to increase effective resolution. You stretch your reach not by moving your body, but by improving your sensors. For Kepler 442b, that turns Webb into phase 1 of what is realistically a multi-century remote sensing program. Webb gives you the first spectrum that says, "This looks inhabited." Next-generation telescopes, some from the ground, some in space, try to confirm and refine that. They look for more subtle gases, seasonal changes, maybe hints of industrial pollutants. Farther in the future, space interferometers could attempt crude maps of brightness across the planet's disk, changes with rotation, hints of continents versus oceans, maybe even differences between day and night. Every step is still just photons hitting detectors, but every step pulls a little more structure out of what was originally just a faint dip in starlight. So, for you and for anyone alive now, visiting Earth 3.0 does not mean starships. It means building instruments good enough that light, and only light, becomes your probe. You accept that your role in the story is not to go, but to see. And that leads straight into a darker, more unsettling line of thought. If we can never touch this world, if our only contact is spectra and maybe a few pixels from future telescopes, what does it mean that it's already occupied? Is that good news or a warning about how fragile civilizations are and how short our own window might be compared to the timescales that Kepler 442b has been quietly alive? Finding another living world sounds like good news. So why does the word occupied instantly make it feel dangerous? The first problem is brutally practical. Even if Kepler 442b is covered in life, that doesn't mean its biology and ours can share the same space without disaster. On Earth, all life uses the same basic toolkit, the same 20-ish amino acids, the same handedness of molecules, the same DNA structure. That shared system is why you can eat plants and animals and turn them into fuel for your cells. On Kepler 442b, there is no reason for life to pick our version of chemistry. Its proteins might use a different set of amino acids. The molecules might be built with opposite chirality, mirror image versions of ours. Enzymes and receptors could be tuned to shapes that our biology doesn't even recognize. To your body, that could make their biomass completely indigestible, like eating plastic. Or worse, some of their molecules might bind to your systems in the wrong way, jamming critical processes, acting as powerful toxins rather than nutrients. Even if the solvent is still water, the detailed chemistry could be so alien that contact is dangerous in both directions. This is not new continent exploration, where you can more or less assume shared biochemistry. This is new biochemistry, with unknown risks on every contact point. So flip the usual exploration fantasy. Instead of asking, what could we do there, you have to ask, do we even have the right to set foot in their ecosystem? Right now, with Mars, Europa, and Enceladus, we worry about forward contamination in a narrow way. We don't want to accidentally seed those worlds with microbes and ruin future science. With Kepler 442b, that concern scales up massively. If it truly hosts a rich, long-lived biosphere, sending a probe that might crash, break open, and spray Earth microbes into an alien ocean becomes a real ethical problem. Those microbes might die immediately because the chemistry is wrong, or they might find some niche and start multiplying, outcompeting local life in certain environments, spreading uncontrolled. We don't know. Planetary protection stops being a technical guideline and turns into an ethical wall. Do not touch the living world with your own biology. If we take exobiology seriously, a confirmed living Earth 3.0 becomes a place we study but never directly interfere with. Not just no humans, but possibly no physical probes that carry Earth life at all. Observation only. And that feels like a loss, because the more alive it looks, the more you want to see it close up. Then there's a pisological hit that goes deeper, the great filter question. You are now looking at a planet that is probably older than Earth, orbiting a more stable star, with conditions that are, on paper, even better for long-term life. It may have had billions of extra years for evolution to climb from microbes to complex life to technology. So you check the big obvious technosignatures, any huge artificial structures blocking starlight, any ridiculous mid-infrared glow that screams, "We built something star-sized," any clear, powerful beacons in radio or laser light. And you don't see anything that blatant. The system does not light up as a clear Kardashev Type 2 civilization using a big chunk of its star's power output. That pushes you into a corner with three main options, and none of them are comforting. Option 1, civilizations are extremely rare. Life might be common, but the jump from global biosphere to tool-using, star-talking intelligence happens almost never, even with billions of years to play with. That would mean we're a freak chance event, and Kepler 442b stayed just biological without ever reaching technology. Option 2, civilizations are not rare, but they don't advertise. They don't build star-spanning megastructures. They don't beam powerful signals. They hide or stay quiet for reasons you don't understand. Option 3, they do arise, they do build and broadcast for a while, and then they don't last. Catastrophe, collapse, or some transition you haven't even thought of wipes out or transforms the visible signature before it ever gets to the galaxy-wide scale. No matter which one you pick, the message is unsettling. If civilizations are rare, you're lonely. If they hide, you don't know why, and you don't know if you should copy them. If they die out, then every living biosphere is sitting on a time bomb, and occupied might mean for now. Suddenly, Kepler 442b stops being just a scientific object and starts feeling like data in a dangerous equation about our own chances of long-term survival. And then there's the time offset that's baked into everything you see. The light you're analyzing left Kepler 442 about 1,196 years ago. Back then, on Earth, the Middle Ages were still in full swing. No electricity, no telescopes, no modern science. So if Kepler 442b does host a technical species, in your data, it is automatically at least 1,200 years ahead of where you are now, simply because you're always seeing them in the past. If they're still around today in their own now, they've had all that extra time to keep advancing. Every problem that looks existential to you, climate instability, resource limits, nuclear risk, uncontrolled technology, they've either solved, transcended, or been destroyed by before you ever got to see it in your data. That split leads to two very different but equally heavy possibilities. In the first, they survived. They learned how to manage their biosphere, their technology, and their risks over timescales you're nowhere near yet. If that's true, they're out there now, somewhere in the Kepler system, operating at a level that makes your current civilization look like prehistory. You are pointing telescopes at their world from across the galaxy without them necessarily even noticing, or maybe they noticed centuries ago and quietly logged us as just starting out. In the second possibility, they didn't make it. Maybe the signals in the atmosphere that look like a healthy biosphere are actually the relaxed end state after a technical phase burned out. Maybe you're seeing a planet where a civilization once existed, changed the atmosphere, and then went silent, leaving behind only a stable post-collapse ecosystem or a slowly recovering biosphere. In either case, occupied stops sounding like a simple victory and starts sounding like a mirror. You're not just learning about them, you're being forced to think about us. If Earth 3.0 is alive, and maybe was or is technological, what does that say about our place in the galaxy, and how do we update our assumptions about how common life really is? That's where the next step hits. Once you have one confirmed living exoplanet in hand, you're not just speculating anymore. You have to plug it into the Drake equation and redo the numbers on how many living worlds and how many civilizations might actually be out there. How do your assumptions about life in the universe survive the moment you know, not just suspect, that another planet's atmosphere is being run by biology? Up to now, the Drake equation has been a thought experiment. You plug in guesses for things like how many stars have planets, how many planets sit in habitable zones, and then the really fuzzy terms. What fraction of those actually develop life? What fraction of those develop intelligence, and so on? Almost all of those numbers are guesswork. The term for fraction of habitable worlds where life actually arises is usually called FL, and it has been anything from tiny to almost 1 depending on who you ask. With Kepler 442b showing a clear biosignature, that changes. You suddenly have 2 data points, not 1. Earth and Kepler 442b. Both are in habitable zones, both show evidence of global biospheres, and Kepler 442b is not some hand-picked neighbor. You're talking about a random K-dwarf system more than 1,000 light-years away that first showed up as a faint transit in Kepler data. If a distant, unremarkable orange star with a good planet turns out to be alive, that pushes FL upward in your mental model. Life stops looking like a freak accident that happened once in a billion tries and starts looking more like a natural outcome whenever the conditions are right and time runs long enough. The Drake equation itself doesn't magically spit out exact answers after one new world, but the shape of the argument shifts. If one out of one or two good candidates you've checked turns out to be alive, you can't honestly talk about life as an extreme rarity anymore. The reasonable default becomes habitable zones plus long timescales often lead to biology. Now the real uncertainty moves down the chain. How often does that biology get to complex life, intelligence, and technology? You've broken the old comfort zone where you could say, maybe life is almost impossible. That escape route is gone. There's also a quieter but heavy shift in how you think about Earth itself. For about 400 years, every big step in astronomy has pushed us away from the center. First, Earth wasn't the center of the solar system. Then the sun wasn't the center of the galaxy. Then the Milky Way wasn't the center of the universe. Even so, there was still one big central thing left. Earth was the only known life-bearing world, the reference point for what a biosphere looks like. Everything else was maybe or probably not. A living Kepler 442b knocks that last pedestal over. Earth is no longer the template for habitable planets. It's just one example in a growing set. You become one data point in a cosmic sample, not the master pattern. Kepler 442b has different gravity, a different star, a different year length, probably different chemistry in its oceans, and yet it still managed to get all the way to a global biosphere that you can detect from 1,196 light-years away. The definition of Earth-like has to stretch. It stops meaning almost exactly like our planet and starts meaning a broad family of worlds that can host long-lived life. Once that sinks in, the cultural and psychological fallout is unavoidable. You cannot drop the confirmed existence of an Earth 3.0 into human society and expect everything to stay the same. Philosophically, the core questions flip. Before, the main puzzle was, why is there life at all? Now, once you see that life appears independently at least twice in one galaxy, the more pressing question becomes, why wouldn't the universe be full of it? If habitable conditions plus deep time tend to produce biospheres, then the default expectation is a Milky Way peppered with living worlds. That leads straight into a second, sharper question. If the universe is full of life, why are we only now getting our first clear external example? And why don't we yet see obvious signs of advanced civilizations shouting across the stars? That's where a new kind of anxiety creeps in. For decades, the big fear in SETI and exobiology was that we might be alone, that Earth might be the only living planet we ever find, and that the universe is mostly sterile. That's a heavy feeling, but it comes with a strange kind of specialness. In that story, we are incredibly rare, maybe unique, and that makes our existence precious. With Kepler 442b confirmed as inhabited, that version of loneliness loses its footing. The galaxy starts to look more like a place where life is a common outcome, not an exception. The fear shifts. It's no longer, what if it's only us? It becomes, what if we're late? If a random K-dwarf system already has a mature biosphere, maybe complex life, possibly even an old civilization, then there may be countless others that have gone through the same arc, some long before Earth cooled. The universe might already be full of civilizations, scattered across time and space, but separated from us by distances and time lags that make real contact almost impossible. You go from fearing an empty universe to fearing a crowded one where everyone is trapped in their own light cones, aware of each other only as faint signals and chemical signatures. That feeling is a different kind of cosmic loneliness. Not we are alone, but we are one of many and still effectively isolated. You might live in a galaxy where life emerges regularly on K-dwarf worlds, builds rich biospheres, sometimes climbs to intelligence, sometimes burns out. You can detect that life in spectra, maybe even see hints of its technology in strange chemicals or radio spikes, but you will almost certainly never stand on its soil, breathe its air, or talk to it in anything like real time. Kepler 442b doesn't just answer the question, are we alone biologically? It pushes you into a harder question. What does it mean to share a universe with other living worlds you can't reach? Once that sinks in, the focus turns back to you, here, now. If Earth is just one instance in a wider pattern of living planets, then the really urgent question becomes practical and personal. Given what we've just learned from Webb and from Kepler 442b, what do you actually do in your lifetime when you're stuck on Earth, but you know Earth 3.0 is out there breathing under an orange sun? The first answer is simple and very practical. You build better eyes. Webb is a pathfinder, not the final word. It showed you that you can read the air of a planet more than 1,000 light-years away. Now the job is to design machines that go beyond just transit spectra. On the ground, you've got monsters like the Extremely Large Telescope, the ELT, with a primary mirror over 39 meters across, more than 120 feet. That kind of collecting area plus adaptive optics lets you try high-contrast imaging, actually separating faint planet light from blazing starlight, at least for closer systems. In space, you start planning missions built specifically for Earth-like planets. Concepts like a habitable worlds observatory are designed to do what Webb can't do well enough: block out a star's light with extreme precision, then pull out the tiny reflected glow of an Earth-sized planet next to it, not just in infrared but in visible and near-infrared wavelengths. That means you don't just see absorption lines from starlight shining through the atmosphere during a transit, you see the planet's own reflected spectrum. You can compare how it looks at different phases, maybe even see crude color differences as continents, oceans, and clouds rotate in and out of view. Webb opened the door. These next observatories are built to walk through it, specifically targeted at worlds like Kepler 442b, even if they can only do that kind of detailed work on closer analogs at first. Once you know Kepler 442b is alive, you also change how you think about time. It's not enough to grab one spectrum and frame it on the wall. You need to watch the planet evolve, even if your entire career only samples a tiny slice of its timeline. That's where time domain exoplanetology comes in. Instead of just "we observed the transit," you move to "we observed dozens of transits over many years and compared them." Tiny shifts in the depths of certain spectral lines, small changes in gases like carbon dioxide or methane over time, could tell you about seasons, climate cycles, even biosphere-scale responses. If methane goes up and down with a regular period that matches the planet's seasons, you might be seeing something like a planetary-scale breathing of the biosphere, similar to how Earth's carbon dioxide fluctuates with the growth and decay of vegetation. If ozone or water vapor features shift in sync with the orbit, you might be catching the signature of clouds, storms, or ice coverage changing over time. The planet becomes a dynamic object, not a static one, and you track it the way we track our own atmosphere, just in much slower and noisier fashion. For the first time in history, you're not just watching a star change over time, you're watching another world's climate tick. To make that really work, you can't rely on one telescope doing everything. You start stacking tools. Radio observatories schedule deep, targeted listening campaigns on Kepler 442, scanning a wide range of frequencies for narrow-band signals or strange transients. Optical telescopes look for laser pulses or odd brightness spikes. Infrared space telescopes, including Webb and whatever comes after, keep doing spectroscopy, chasing both biosignatures and potential technosignatures like industrial pollutants. Maybe you even bring in X-ray and ultraviolet observatories to monitor the star's high-energy behavior, so you can correlate flare activity with any sudden changes you see in the planet's atmosphere. Over time, Kepler 442b becomes a permanent fixture on observing schedules. It turns into the exoplanet equivalent of the Sun or Jupiter, a system that every new generation of instruments checks in on. Students grow up knowing its light curve and spectrum the way earlier generations knew the phases of Venus. It's not one target among many anymore, it's a shared benchmark for what a living exoplanet looks like. Every new telescope adds another slice of information, and together they build a multi-wavelength, multi-decade portrait of a world that nobody will ever visit, but everybody studies. And then there's the cultural hit, the image that replaces the old one in people's minds. When Carl Sagan called Earth the pale blue dot, he was reacting to a Voyager photo that showed our planet as a tiny single pixel in a sunbeam, a lonely world in a huge dark field. That picture carried a certain story. This is us, alone, fragile, unique. In an era where Kepler 442b is confirmed as Earth 3.0, that story changes. Pale blue dot stops being a singular phrase and becomes a category. You now live in a universe where there are multiple dots like that. Some may be more blue, some more green, some darker under orange suns. All of them separate experiments in how life can rework a planet. New images, maybe crude direct imaging snapshots or future interferometer maps, show you other tiny points of light that you know are not just rocks. They are worlds with oceans, skies, and chemistry that has been running for billions of years. Kids will grow up not with one special dot, but with a mental map that includes Earth, Kepler 442b, and whatever other living worlds we find next. The emotional baseline shifts from we are alone on a single island to we are one island in an archipelago we can see but never reach. In your lifetime, your role is to help build that map, even if you're just watching from the outside through a screen. You push for better telescopes instead of fantasy starships, for smarter observing strategies instead of quick hype. You accept that for now, light is your only probe, and you use it as hard as you can. Earth 3.0 is out there, already occupied, already deep into its own story, and for the first time, you know enough to say that with a straight face. The next step is simple and heavy at the same time. You keep looking, because if one distant orange star hid a living world in its noise, there is no good reason to think it's the only one. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.